Hello. Today I have some pain relief medication. Its active ingredients is acetaminophen and ibuprofen. And according to the box, I should take 2 caplets every 8 hours and no more than 6 in 24 hours. And so the question for this section is, where do those numbers come from? And how do difference equations help us model that? Because if the active ingredient gets too concentrated in our system, that's not good for us. And if it gets too diluted, then it won't be effective. So there's a sweet spot in there, and we can use difference equations to help us find it. Another example of a real-world question that is helpful to use difference equations modeling is population growth. And so the example we're going to look at first is the wildebeest in the Serengeti. And so the question is, can we model the number of wildebeest in the Serengeti by year? Now, here's some data to give you an idea of what we're talking about. It goes back to 1959, and we can see in that year there was 212,000 wildebeest, and it's only gone up since then, at least up to 1977. So both the medication problem and the population problem have in common that we can use difference equations to model it, but it's not going to be as precise as the financial examples we did in the last section. So that messiness is going to have to be simplified down using some assumptions. And so let's focus on the population problem first. And so we're going to define the problem. And as you can recall, that means we need to brainstorm all the different things that go into population growth and try to narrow that down into something we can manage and model. So pause the video, think about all those variables, and then see what you come up with. And we'll talk here in a moment. All right. Well, hopefully you thought about things like disease and famine and immigration either in or out of the Serengeti, if that's possible. We would need some research to handle all those things. But the biggest variables that are going to affect population change is going to be births and deaths. And hopefully that birth rate and that death rate are relatively constant for a wildebeest population. But we won't know till we model it. So let's use that as our main assumption, is that we're going to assume that the change in population of the wildebeest is proportional to the current population. So notice this works actually for any population. Well, hopefully it's true for wildebeest, is that the more wildebeest we have, the more babies there's going to be. Or the more wildebeest there are, the more deaths there's going to be. And if those numbers go down, then the change should go down as well. So that seems like a reasonable population, reasonable assumption. Now, what's the relationship? We're going to assume proportional. That may or may not be the best relationship. But because we've learned that in the previous section, we'll start there and see how it goes. So let's build the model. So since we're going to build the model, we need to let P sub n equal the population of wildebeest after n time periods. And in this case, it's going to be 2-year time periods. Since 1959, because that's what our data gives us. So here's our data. And notice this is an important detail, is that these must be equally spaced. Right? If these aren't equally spaced, then the iterative process that we use in difference equations won't work. We'll have to do some other technique if that's the case. So fortunately they're every other year, so we're fine there. And so now we can convert our assumption into an actual model. And as you'll recall from the previous section, change in population means that delta sub P sub n is going to be equal to something. And because proportional, that means we're going to have a proportionality constant. We'll call it R. And then the current population, well, that's just P sub n. So this looks a lot like our bank account example from last section. And just like that section, we need to have an initial value because this is a recursive formula. And so we have to have a place to start. And in our case, P0 is going to be the first data value because n equals 0 corresponds to 1959, and n equals 1 corresponds to 1961, and so forth. So here's our model. But it's incomplete because we have this assumption of proportionality, but we don't know what R is, and we need to find R. Now, so far, this has been a theory-driven model, right? Our assumption was based on a theoretical and intuitive idea, but we do need some data to calculate R. Maybe if we knew more about wildebeests, we could come up with a theory-driven value for R based on births and deaths and how that works. Maybe we talk to an expert, we could do that. But with the limited information we have, we're going to have to do this with just the data. So how are we going to find R? Well, notice if I solve for R in this equation, I get R equals delta P sub n over P sub n. And so what I can do is I can calculate the change for each one of these and see what we get. So for example, the change of these first two is 51, and the change of these last two data points is 218. And so that would be in my numerator, and then the P sub n, I would just be dividing by each one of these values as we march down the data values. Hopefully we'll get a constant, but we'll have to work it out and see. Now, once we get that constant, then we can actually work out a formula for our model, because this is not a final answer that's useful. It's easier to think about this as P sub n minus P sub n plus 1 minus P sub n is equal to R times P sub n, or what's the same thing, P sub n plus 1 is equal to P sub n plus R times P sub n, or finally 1 plus R times P sub n. So this will be our model. So overall then, our model is P sub n plus 1 equals 1 plus R Pn with P0 equaling 212. Now, to finish building the model, like I said, we'll need to find R, and then we'll need to analyze it. And we'll save that for the next video, where we'll use a spreadsheet to help us with both those things. We'll see you there.